Hi, and welcome back to Codex. Our talks this summer feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today, we have Dan Packer, who is a PhD student at The Ohio State University. We are happy to have him here today to tell us about max filtering with reflection groups. Take it away, Dan.
Thank you so much for the introduction, and thank you to all of the organizers for making this happen and for organizing this whole thing over the summer. It's really cool. I'm a big fan. But yeah, I'll jump right into it. So this talk's going to be about max filtering with reflection groups. I'm going to first start us off with some motivation. Then I'm going to tell you what the title of the slide of the talk means, because maybe you don't know what max filtering is, maybe you don't know what reflection groups are. I would say about 2 years ago, I didn't know what either of these things were. So I don't know where you're at, but that's where I was at until somewhat recently. So first, here's the motivation that I give when people who are non-mathematicians ask me like what I do as a mathematician, and they're like, oh, like what's the applicability of what you do? And the story I tell is, imagine you're a self-driving car and you see a stop sign. Well, you've got some giant AI ML algorithm that's going to tell you that you should stop when you see a stop sign. And that is great. And we love it. You have a lot of sample images of stop signs around the country, and everything's great. But then something might happen, which is a stop sign is knocked on its side a little bit. It's still a stop sign, but maybe you didn't have a training image of a stop sign at that particular angle. Maybe all of your stop signs were like perfectly right side up, or maybe at a little angle, or maybe at just a different angle than one of these. And so we might want to know that we're actually going to stop at the stop sign and we're not going to blow through it, even if it's at a slight angle. And importantly, we want to do this quickly because we are a car and we are going fast, and we would like to actually be able to identify our stop signs. And we would like to be able to do it reliably. Like we want, if like a regulator shows up and is like, your cars aren't stopping at stop signs, we would like to actually be able to say, well, it's definitely not because they're at a slight angle. And so we really want fast and credible classification of objects that maybe have some symmetry applied to them. So that's the basic structure of what we're going to do. The way we're going to answer this is building off some research with Dustin, my advisor, Jameson, and Joey. And Joey is not, I mean, I know Joey's in the audience. And then this particular project was work I did with my advisor, Dustin, who is also, I think, the only person with their video on. So I'm going to give you a basic structure of how this talk is going to go. I'm going to tell you what max filtering is. And I'm going to tell you what reflection groups are. This should be great because that's the title of the talk. So by bullet point 2, you'll know what the talk's about. And then I'll tell you about like the progress we made. And then we're going to talk about like some of the takeaways that you can use maybe in related research that you're doing. Because maybe, I mean, I think there's a lot of value in just like going to a talk and finding like a thing worth thinking about. So first, let's start by talking about what max filtering is. Before we do that, I'm going to tell you about like, I'm going to like nail down that motivation from the beginning a little bit more precisely. So in general, in machine learning, it's very nice to have these large architectures because they can be very expressive. But it's not nice to have these large architectures because they are very hard to interpret. We don't necessarily know like how a deep neural network is going to classify something. And so this is that example. It's nice to know certain things for sure. It's nice to be able to say, to know for sure that if you do well on one sort of stop sign, you're going to do well on all of the other versions of stop signs. And what you might say is like, okay, well, if I'm building my deep neural network, well, then I'll feed all of these rotated images of these stop signs in as well. And then I'll just work on all of those. And this method is called data augmentation. And it's great, but it misses some key points. For instance, this group that we're talking about in this case is sort of infinite in the sense that like it's still a discrete problem, but you've sort of got like a lot of rotations that are available. So it's very hard to augment your data set with every possible rotation of a stop sign. And secondly, even if we do that, then we have to analyze our loss for the entire, our loss function is now not just saying how accurate we are on one stop sign, it's really saying how accurate we are on average over all stop signs. And that's just maybe a bit harder to interpret. So we want some architecture that actually sees these different objects as exactly the same thing. And the hope is by having them be exactly the same thing, then we'll have a bit more credibility in our algorithm, in our predictions. And so there's sort of two ways to do this. You start with some data, you can do machine learning on it, and then make your machine learning architecture group invariant. You could say average over the inputs, or feed in extra data, which is rotation, like rotations of your data. That's sort of the data augmentation. Or you can sort of apply what's called the Reynolds operator, where you sort of average over the orbits. And that's on the second path to the left. This path to the right is you say, okay, you know what? I actually don't care about the particular representative of an orbit that I have for my symmetry. Like I've got some symmetry, and I don't care like the particular rotation of my stop sign. So I'm going to try to take my stop sign images and transform them into something that collapses every possible rotation of a stop sign into a single data point. And then we can do machine learning on that. And then we have a lot more rigidity in our structure. It's a bit more algebraic of an approach. And so we like the second one, but I mean, this isn't like an overall value judgment. You should like whichever method appeals to you more. Well, I'm not saying that like there aren't great approaches to group invariant machine learning that take the first approach. I think there's good research on that front as well. Just in your mind, it might be helpful to draw this separation, and I want you to think about this path on the right as what we're going to talk about today. So when I say group invariant machine learning, we need to decide like what we actually want it to do. I'm going to work from our motivation from before, and we're going to try to make the three things about group invariant machine learning. We're going to have like sort of three desiderata. I can never pronounce that word, but like we're going to have three goals. And there's these three goals of what we want group invariant machine learning to do. We want it to be group invariant. We want it to be good for machine learning, and we want it not to take forever. And that's the basic idea. I want to make these precise down below. So first, to be group invariant means that if I have some action of this is the first mathy slide, I apologize. If I have some group action on my data points, my function shouldn't care which element I get. I should be able to spin up my elements by any group, my data points by any group element, and I should still get the same output. Now, the second bullet point, this is one of the big ones that like determines how you go about doing your group invariant machine learning, is what you mean when you say preserve structure that machine learning cares about. In our case, we're going to focus on metric structure. So a really natural thing to think about is being bilipschitz. This means that when we process our data in a group invariant way, we don't shrink or grow distances very much. And we do this by sort of taking the ratio of the distance before and the distance after. I guess is the distance after and the distance before. And we make sure that that's bounded by constants that don't depend on the inputted data points. Notice that the distance in our domain is the group invariant distance, so it's the quotient distance. It's not the distance just in RD, it's the quotient distance for our group action. And then finally, we want it to be fast, and sort of the baseline speed we want our algorithm, whatever structure we have, to be faster than just computing every possible pairwise quotient distance in our data set. Because you could just do that and then do MDS. If you're trying to like hit goals 1 and 2, and then you're trying to hit 3, you could just like compute all your pairwise quotient distances and then like do a variety of different dimensionality reduction techniques, and you'll be good to go. So we want to be fast. And so this is our goal. And the solution I'm going to give you to this depends on having all three of these be your goal. Like if you remove any one of these, then max filtering is no longer the thing for you. However, I think these are a good set of things to want. So hopefully you're convinced that this is a thing worth caring about. So Now I'm going to tell you how to do this thing. So the hero of this story is called max filtering. And on this slide, I would like you to think about max filtering as sort of a measurement scheme. So what I do is I've got some data point X, and I want to understand X in a group invariant way. So what I'm going to do is I'm going to measure it against some template T. So X is my data point, T is my template. They both just live in the space. And what I'm going to do is I'm going to try to line up X and T as best as I can. So maybe there are two like sound waves. I want to overlap them so that their inner product is the largest. So I'm going to translate the two sound waves to be overlapping. And I'm going to take that inner product, and that's going to be my measurement of X against T. So this is sort of like where it's measurement in the sense that like inner products form the measurement. And then what we're going to stack onto this is what we call a max filter bank, where we take a bunch of different measurements. We don't take a single template, because a single template wouldn't be enough, right? If we take a single template, the max filter of just one template just gives you a real number. So we're going from RD to R. That's definitely not going to preserve enough structure. So we want a bunch of these. We're going to take a bunch of measurements, stack them up, and that should tell us about some structure that we care about. And so that's the idea of a max filter bank. You pick some clever sets of templates, or maybe you don't, maybe you just randomly pick templates. Lots of options available here. You pick some templates, and then you take your measurements of X against each of those templates, stack them up into a vector, and that's your map. You'll have questions about this. I haven't paused once since we started, so maybe I should give you guys a second to ask questions or comments. Cool. I'm going to give you some other pictures of this later, so if you're confused or feel like, I don't really understand what's going on, that's fine. You'll eventually understand what's going on, I promise. So anyway, so we've defined this thing. What does it do? So max filtering, that's the definition up top, does the things we want it to do. So it's group invariant, that was bullet point 1. It's bilipschitz, that was bullet point 2. And bullet point 3 is the goal of the previous one. We need to compute the number of templates times the number of data points quotient distances. Versus if you wanted to do just MDS or something, you would just need the number of data points squared worth of quotient distance computations. And as long as your data set's large, this is great. And then you get this nice embedding, and then you can just compute distances in the as vectors, and it's nice. And on this slide, I want you to sort of notice that the symbol we use for max filtering looks a lot like an inner product, and that's not an accident. It looks like the inner product for the quotient distance. It satisfies what I believe is called the polarization identity. I always forget if that's actually what this is, but it satisfies a parallelogram-ish thing that also the inner product satisfies. If I remove the G here and remove the G here, and I remove a set of angle brackets, and this is just an inner product factor. And it's got a lot of nice theoretical properties. And it's nice to have that because then you can leverage that, right? So many machine learning tools are effective, but don't have good theory. And the goal of this is we're going to have good theory along with our good actual practice. So we're going to get a nice combo, and that's going to be fun. So that's what this is maybe the selling point of max filtering is it hits our desiderata, but it also has nice theoretical properties beyond them. But be warned, sometimes computing max filters can be hard. I'm allergic to a bazillion different things, and so I always read the may contain on the ingredients. So be aware, max filtering is not going to suddenly solve all your problems. You still need to be a little bit aware. You need to read the package. So figuring out what a quotient distance is, because computing max filter is just as hard as computing a quotient distance. Computing quotient distances is sometimes hard. You might have to do a fast Fourier transform if you're talking about cyclic translation. You might need to solve a linear program if you're talking about point clouds. You might need to solve graph isomorphism if you're talking about being symmetric to removing the vertices of a graph. So max filtering is applicable in all these settings, but in some cases it's maybe not a panacea. You still might have to solve graph isomorphism. So like, we want to look at cases where maybe computing max filters is easy. And spoiler alert, reflection groups are one of those contexts where solving a max filter is actually incredibly easy. And we're going to try to make a point that it's easy and it's effective and it's got nice theoretical properties. It's just like everything you want out of a numerical method. So we'll see that yet to come, but that's the basic idea. And it's just worth pointing out there's a lot of related things out there. The work on max filtering was particularly inspired by the landmark embedding idea of morphometrics, and also sort of is, I don't want to say a competitor, but it like tries to solve similar problems to how moment methods of like the bispectrum try to work on cryo-EM. And then you have things like the scattering transform, which is pretty direct inspiration, and the maxing idea in a max filter is inspired by the max pooling layers of convolutional neural networks. And I guess I didn't talk about the linearized optimal transport one, but linearized optimal transport leverages a very similar idea where you have like a reference measure and and you see how to align with your reference measure and that gives you an embedding on its own. So there's like linearized optimal transport is the same, but it has similar vibes. But so if you happen to know about it, I would think about it very similarly. It's a way of embedding your quotient space, not embedding, but like mapping your quotient space to just a Euclidean space in a way that preserves a lot of structure in the same way as LOT does. But yeah, okay. So I believe that's our max filtering section. Now we can talk about reflection groups. So we'll have the full title of the slide done. So before I do that, I'm going to show you some pictures. And hopefully these pictures will help you understand max filtering better. And will also maybe give you some intuition for why we think about reflection groups when we think about max filtering. So what I'm going to talk about first is I'm going to talk about a group that's not a reflection group. This is a rotation group. We're going to have G be a set of 45-degree rotations, and we're going to max filter over G. So I've got a template T, and so for any given X, if I wanted to max filter an X with T, what I would do is I'd take my vector X and I'd rotate it to be as close to T as possible, and then I'd record their inner product. That's how you do a max filter. But alternatively to that, you can also take T and you can rotate it to whatever X is. So if X was over here, I could take T and rotate it over to be close to X and then record their inner product. So now I can see that I can take my T's and I can sort of split up my space, and I can split my space according to which version of T I should move to for a given X. So if my X is in this wedge, then I should line up to this copy of T, or this element of the orbit of T. If my X is over in the lower right, then I should line up to this copy of T, etc. And so what's actually happening here is these different elements of the orbit of T are splitting my space up into Voronoi cells. Incidentally, these are also fundamental domains, if that term means anything to you, of your for your group representation. That is, every orbit is represented by exactly one element in this Voronoi cell, up to some issues with the boundary. So like there's issues with the boundary, we're going to just ignore the issues on the boundary. So this green area is a Voronoi cell and it's a fundamental domain. I'm going to call it a Voronoi domain for the purposes of this talk, but that just means it's a Voronoi cell and a fundamental domain. This is not like a term anyone else uses. And I want to just watch how this Voronoi domain moves about when I move T. So as I move my template, my Voronoi domain moves. And this is a thing we were actually doing when we were first thinking about max filtering, is like, how does the Voronoi domain depend on my choice of template? And in this case, it's very natural. Like I move my template a little bit, my Voronoi domain moves a little bit. And so far, everything's great. I'm going to do the same exact thing, but now with two different groups. On the right-hand side is the same exact picture I just showed you. On the left-hand side is a different group. Instead of 45-degree rotations, it's going to be 45-degree reflections. And by that, I mean reflection about the x-axis, about the y-axis, and sort of an x additionally. So like the line y equals x and the line y equals negative x. And so I'm reflecting over all of those. And so I'm just going to do the same thing. So I take t, I spin it up to its orbit. Already you can see the orbits look different. And then I can split my space up into Voronoi domains. And take one Voronoi domain. Now as I move, and already you can see the Voronoi domains are different. So if I'm lining things up to t on the left, I do a different thing than if I was lining things up to t on the right. And so I can move t around, and its Voronoi domain moves in both cases. However, on the left side, we can see we're just sort of like lighting up different wedges. The structure of the wedges never changes. I'm just picking the one that I've lit up. And if I move t by a little bit, the Voronoi domain doesn't change at all. Whereas on the right, like the Voronoi domain moves, but on the left, it doesn't. So that's kind of cool, pretty nifty. This is one of the key properties we noticed about particular groups like 45-degree reflections. It made us think, oh, maybe there's something special going on here. Maybe this is going to be helpful for max filter. So now I'm going to give you another example. I feel like this is like a rhetorical move people do. They're like, oh, I'm going to give you one example, and I'm going to give you a completely different example with no transition. And then it's going to be up to you to find the connection. So that's the idea of this slide. So I'm going to give you a different group. I'm going to think about vectors in RD. I'm going to allow to permute their coordinates. So if I've got a vector like 7, 2, negative 14, 1, I'm allowed to just like resort their coordinates willy-nilly, and 5, negative 3, negative 5, 10. I'm just going to like get to rearrange them. And how do I align them? Like I'm allowed to just, I've essentially got like 2 bags of numbers. I'm going to pour them into these vectors. And I want to line them up in some fashion to get the largest inner product possible. And I'm going to give you guys like a minute to think about this. Like, because in retrospect, to me, it's now obvious how you do this. But in actuality, I think it's not immediately obvious. So it's worth thinking about what the strategy is. So take a second and just think about it. Also, this is an opportunity to just, I don't know. Yeah, so I'm going to tell you the answer in a second, which is, okay, now I'm going to tell you the answer. So I guess if you're watching the video online, you could pause it, but if you're in person, you can't pause VLA, sadly. What we're going to do is we're going to sort of do a greedy algorithm. I'm not going to prove to you that it's the best thing to do. There's a couple different ways to prove it, but they're all like, they take a little bit of work. They take more work than I feel like it should take. So what we're going to do is we're going to take the largest element in X, the largest element in Y, and we're going to line them up. So that's going to give us a lot of bonus points, right? Because if I want to line 7 up to something, I want to line it up with the biggest thing on the right. And because it's multiplicative, I get the most bang for my buck when the largest thing on the left and the largest thing on the right are lined up. And then I'm going to repeat. I'm going to take the largest thing on the left, which is 2, and the largest thing on the right, which is 5. I'm going to line them up. And then the largest thing on the left is 1. The largest thing on the right is negative 3. So I'm going to line those up. And then negative 14 and negative 5 get lined up, and their negative signs cancel, and we get a lot of bonus points for that. And I don't think it's like, there's a lot of thinking one has to do about like, oh, this negative numbers mess things up. What happens when you have 0? And there are a couple of ways to think about it. Happy to answer a question about that if people are like really curious. But this is, I promise, how best to line them up is you take the largest one of each and you line them up. So that's how we line this up. But now let's think about this a bit more carefully, because this still would take a while. It's like you have to find this biggest one on one side and the biggest one on the other side and line them up, and you do the next one. It takes a while. Let's try to do it better. Well, like if X is already sorted, which I've done here, I've sorted X in an ascending fashion. Well, then to line it up with Y, I just need to sort Y as well, right? And that, because then my alignment just goes across, and that seems great. And so the point is, we can do this entirely independently from each other. We can line up X and we line up Y, and X and Y don't have to see each other at any point. We just line them up and then we take an inner product. So this is feeling great. This is not something we can do with rotations. With rotations, you actually have to know what you're aligning to align to it. But in this case, we don't actually have to care about what we're aligning to. We can just align. So that's kind of magical. And I want you to think about like maybe how that's related to the picture. Right now I've done something algebraically. We had a picture. So an important point is that the Voronoi domain of X, if it's sorted, Well, to get y lined up to x, I sort it. So the Voronoi domain of x is just all sorted vectors. And importantly, if I move x by a little amount, it's still sorted. So its Voronoi domain is still the set of sorted vectors. I mean, I'm assuming x is like in the interior of sorted vectors. It's not like degenerate in any way. But this is kind of magical. And this would really remind you of the previous picture of when for the reflection group, where I was moving t by a little bit, and its Voronoi domain didn't move. So that's what's happening again. So there are some things that are happening in both of these examples where we sort of have a canonical choice representative. We could, for instance, in the first case, map all our vectors to be in a particular wedge. We can pick a wedge and then just map all our vectors to be in that wedge. We can just map all our vectors to be sorted. And that there's a canonical, that's my bad. There's a canonical choice that defines a Voronoi domain. And by canonical, I don't mean like a singular one. I mean that you can choose one to be canonical. And it turns out that mapping a vector according to some canonical choice, as in like by sorting, I want you to think about the canonical choice as sorting or something similar, you actually get an isometry. I didn't show you this, but it's true, so you can believe me, and that's pretty cool. And this doesn't hold for any group, right? This is, if you look at the 45-degree rotation example, like none of these are true. There's no canonical version of a vector in the same way. So this is magical. And what are these groups? They're reflection groups. So a reflection group is kind of what you might think. So you take a vector, and then you look at the plane orthogonal to it, and then you think about reflection through that plane, and that gives you a reflection. And then you just, that's a reflection is an element of the orthogonal group. You take a bunch of those, you throw them all together, you look at the subgroup of the orthogonal group that they generate, and that's what a reflection group is. Quote unquote easy definition. In practice, in this talk, we're going to talk about finite reflection groups because we're doing like data science, and infinite reflection groups are both scary and not as applicable because eventually a computer just has finite amounts of data on it. But so yeah, so we're going to think about things in terms of a finite reflection group. There is interesting things to think about in the infinite case. I just haven't thought about them. So some warnings. In general, right, groups and group representations are not the same thing. But in our case, reflection groups are the representations. They're really subgroups of the orthogonal group. They're not like abstract groups. Coxeter groups provide, every reflection group is the abstract group that's related to it is a Coxeter group. Not all Coxeter groups are reflection groups. And there's other things. I'm for some reason now regretting including all of these different things. There's a lot of things that are bothersome about this because they don't necessarily line up with the words you learn in representation theory. Like the term irreducible representation does not mean the same thing as irreducible reflection group. You need to use the word essential to say that there's no trivial component, stuff like that. And also reflection groups can have rotations in them. They just are generated by reflections. Okay, I'm just making sure that this is not a thing I need to. Cool. Great. So that's some warnings. And here are some examples. The dihedral group of order, that's the 45-degree reflections. Talked about that before. Symmetric group acting by coordinate permutation. That was the other thing we talked about. Can also do coordinate-wise sign flips. That means just like you can make any coordinate positive or negative for free. You can also do like sign permutations, which is really a mixture of bullet points 2 and 3. So in total, there aren't that many finite ones. They've been classified by a guy named Coxeter. Maybe you've heard of him. And they've got some symbols, and these are all finite reflection groups, just all of them. We're looking at them. And we'll eventually use these symbols to describe some of our results, but this is all 5 set sorts. And we're going to look at a particular example, it's going to be the first example, which is symmetric group. I'm going to try to justify to you that we should care about max filtering with these. So an important point is that actually when we're doing max filtering, we don't need to get the group of symmetries perfectly right. And that's because if we have a bunch of other groups that will approximate the structure of the metric, of the quotient metric of a particular group, then that actually extracts enough information, and we can do that maybe faster. We might be able to max filter over that group faster. And reflection groups are going to be exactly this. So the idea, we're just going to find a set of groups that are as descriptive as maybe the group we're actually looking for, and we're going to max filter over those groups, and we're going to take those numbers out, and we're going to use those instead. And hopefully that will be enough signal. So here's the example. We've got some textures here, and each texture has a symmetry, which is that I can translate it in the 2D plane, and it's still the same texture. I can like sort of rotate it around vertically or horizontally, and I still have a texture. I still have the same class of texture. The classes are the same. But instead of using max filtering over that space, which is kind of hard, you have to do some fancy Fourier stuff, the computation gets really messy. What you could do instead is you could max filter over all the sets of permutations of subsquares. So you could take a subsquare of this and just allow any sort of permutation mixture and max filter over that group. And this might sound absurd, and I think it does. And you do this on different scales. And the point is, max filtering over those groups are reflection groups. And so it turns out we can do it really quickly. And in fact, it's not just quickly, but it's really accurate. So for this example, we're going to take a bunch of samples of this set, and we're going to try to predict. And there's a table of how accurate we get. When we do sort of a standard machine learning, it's PCA, LDA, after we max filter over this weird set of groups, we get a much higher accuracy than even a convolutional neural network. And particularly, I want to draw your attention to like 4 points per class, we're 95% accurate. And this is in contrast to a convolutional neural network that just doesn't have enough data yet to understand the structure. But we can tell the algorithm what structure we want in this model. Like we can say like, oh, there's this sort of symmetry, and then it needs a lot fewer data points in order to use that symmetry. So this may be some motivation of why max filtering with reflection groups is good. It works well in practice, and it's fast in practice. I'm about to show you that it's theoretically valuable, like it's theoretically interesting. So before we do that, I just have to tell you some words that I'm going to have to use to describe our results. So this thing that I was calling a Voronoi domain for a reflection group, it's got a fancier name. It's called a Weil chamber. And they have bounding hyperplanes, right? This Weil chamber has this hyperplane and this hyperplane, that's beta 1 and beta 2. You can look at the orthogonal vectors to this hyperplane that point into the cone. And those are what are called a fundamental system. Fundamental systems turn out to be fundamental to the study of reflection groups. No pun intended. And we'll use them to frame our results. Okay, so now I think we're ready. Here are some main results. So I keep doing this. I keep fooling myself. So I'll leave just a reminder about what it means to be bilipschitz. It means you preserve the metric. So this is what's going on here. We're preserving the metric, right? Up to some constants. And we want to quantify how well we can preserve the metric given a group. So we're going to define a thing called the condition number of a group, which is the best max filtering we can do. So we're allowed to take we're infamizing over any choice of templates. We could take maybe a billion templates, not a bazillion, but like a billion templates. And we would want to make our max filtering as good as possible. We want to see we want to make this number as small as possible. And in general, this seems like a very hard thing. You can maybe put upper bounds on it by just picking specific sets of templates. But in our case, we're actually going to put hard bounds on it. So previously, we were able to show that for any group, once you take enough templates, you can get bilipschitzness, which means you have some bound on this. Some bound on kappa of G means you're bilipschitz at all. We want it to be smaller, but Some bound is good. I think this has been improved, but I don't know the exact numbers on it, so I'm not going to say that for sure. But what we're going to do, we're going to do really well. So you see that scary expression. Now it's a much less scary expression. And in fact, for most reflection groups, it's a not scary expression at all. So we're able to get the condition number of our max filtering. So this is the bilipschitz constants down to just the dimension of the size of the group. So that feels great. Or actually, sorry, the dimension of the space. So pretty exciting, except for like one particular case, which is the dihedral group, which is that. So here are our results. So suppose you're trying to max filter over a reflection group. What you want to do is you want to look at the fundamental system, which is that thing I mentioned earlier, that's intrinsic to the reflection group. And then you take your fundamental system, which is a bunch of vectors, you stack them up into a matrix, you look at the largest singular value of that matrix, you look at the smallest singular value of that matrix, and that's the condition number of your max filtering. You might notice that this is also just the condition number of the matrix. And that's not by accident. And in fact, the optimal templates are given by the dual basis. So that's the inverse of your fundamental system. So that's pretty great. Some key observations of this fact that I think are surprising are that in general, you only need D templates to do your max filtering over your reflection group. This is surprising because we are allowed to, in our computation of kappa of G, we're allowed to use as many templates as we want. We are literally allowed to choose like 1,000 different templates. And it turns out that for a reflection group, you only need D templates. There's no way to do better than that. And in general, you need a lot more templates for that. And additional templates aren't going to actually help you at all. Like you just take the D best templates, which are the columns of A inverse, and then you're done. And that seems pretty great. And so once you know how to do that, then you can look at some of the asymptotic properties of the various Coxeter groups. We can just go through the classification and see how the condition number depends by computing what sigma max of A is and sigma min of A is. So it turns out that max filtering over most reflection groups goes with sort of not the order, but the index of the Coxeter, of the reflection group, which I'm indexing as Coxeter groups just because that's the way they're classified. So remember, AL is the symmetric group, for instance. So the point is, as I add an element or as I add a dimension to my vector, I get 2 over pi worse at max filtering, at preserving the metric. And that's what that's saying. And similar things down here. So max filtering gets harder as the size of your group gets bigger. But we now understand exactly the extent to which it gets harder. And we know there's no like special tricks or tips we can do. This is as good as it gets. So here's some tools for you to take home, for you to use, that we used in proving this. So our key proof moves were the main like inspiration step was the idea of sorting and how we generalize sorting to reflection groups. And that's this idea of taking a canonical representative and then focusing on just that specific Voronoi domain / Weil chamber. We take up canonical, we just focus on all the canonical representatives of our space and we work on optimizing in that setting. And we do some convex programming by optimizing our templates restricted to this cone, which is the only cone in which anything works. And our solution to that task was inspired to the scalable frames idea that Cahill and Chen produced like a while back. The citation is the end of this paper if you're interested in that. It's pretty cool stuff. And then we do a fancy thing where instead of looking at trying to show a property of an optimizer of a convex program, we actually do a weird move where we will look at the dual of that program and showing a property of the primal is the same as showing that a particular relaxation of the dual also satisfies the desired properties. Or that the relaxation is tighter. And it's kind of fun. It changes the goal of your proof strategy, and I'll show you what I mean by that in like 2 slides. And then there's also a fun spectral phenomenon that we've actually pinned down now. That's specific to real finite reflection groups that helps us chase out some facts about the spectral properties of reflection groups. So here we go. I'm going to show you the coolest part that I thought of our proof, which is we ultimately, in part of our proof, are trying to show. So this is like the tool that I want to tell you about in the hopes that you bring it home and then you get to use it. So the idea is, suppose you've got some convex optimization problem. You want to show that it satisfies a property. Well, a thing you might do is you might restrict your convex optimization problem to have that property, and then you try to solve it, right? And you try to show that the restriction has the same value as your primal. So, or like the restricted primal has the same value as your primal, and then you show, and then that may be, that's the setup we at least have. And then you can say like, oh, like maybe not every optimal thing in my primal works, but there always is an optimal thing in my restricted primal that works. So we want to show that. But instead of doing that, what we're going to do is we're going to look at the dual problem. And for any restriction, there's a corresponding relaxation. And then sometimes it's actually easier to show that the relaxation has the same value than it is to show the restriction has the same value. So that's to show, instead of showing that the restricted primal, that the value of the primal is feasible in the restricted primal, you can instead show that the value of the relaxed dual is feasible in the dual. So you're sort of going in a different direction. And then you can use strong duality, and that shows you that your restriction doesn't actually change the value of your program. So that's the picture. Now I'm going to show you like a particular example. There's going to be a lot of stuff on this coming slide. I want to warn you, but it's going to be okay. We're just going to focus on like a particular part of it. We're not going to like look at all of it. So the thing that I want you to see here is we've got this convex optimization program somewhere deep in our proof. We want to show that the optimizer is diagonal. So this is the setting we had before. We want to show that, or that there is an optimizer that is diagonal, rather. So what we could do is we could restrict it. We could be like, okay, well, now let's restrict to our optimizer being diagonal, and see if we have the same value. And this is hard to show that these two have the same value. Instead, what we can do is we can dualize. This turns out to be the dual of the program. It looks disgusting. And what we can do is we can then relax it to, in the corresponding way, to have the diagonalness. Like we can look at essentially the dual of this guy, and that's going to be a relaxation of this guy. And then what we need to just show then is that the optimizer of the relaxed dual is also an optimizer of the dual. So instead of showing that something was diagonal here, we have to show that the optimizer is in this set, which is, if you're interested, the completely positive matrices of size D, which maybe is also hard, but it's different at least. And maybe it's easier than showing a different thing as diagonal. And that's the idea, is by passing to the dual and looking at relaxation as opposed to restriction, we've changed the thing we need to prove entirely. It's just a completely different goal. And it turns out this is an easier goal because then we can interpret things as positive definite forms, or sorry, quadratic forms, and like ask about being positive and such. And maybe this is easier. In this case, it was. In this case, this was the move that worked. I'm like, it's kind of a lot of rigmarole to go through, but it's a cool tool. And I would recommend using it because it's very fun and it feels very satisfying when you get to use it. So this is the particular strategy that we used. And like step 3 is the particular point where we got to use this sort of dual relaxation thing. Is we were doing like standard convex optimization things. We use spectral properties because we're dealing with matrices, and that's pretty normal. But then we wanted to look at a quadratic form, or we wanted to show this diagonal thing, and it was actually easier to pass to this relaxation so we can interpret something as a quadratic form and work on it. And that was kind of nifty. I'm obviously glossing over this quite quickly, but like the particular details don't matter. But like I want to really emphasize that this is actually a useful tool. Sometimes it won't work directly. Sometimes you want to look at your relaxation and try to work with that instead. So yeah, okay, we've made it. I'm gonna just emphasize some key points, and then I'll be ready to answer some questions. I guess I also have some questions we can ask at the end too. So back at the beginning, I was really like this whole line of research is entirely predicated on it being valuable to do group invariant machine learning, and in particular to do your group invariant machine learning in a way where you invariantize your data before you even start doing any machine learning, where you have sort of a pre-processing, like a data processing step. So I hope I've convinced you with the stop sign example that that's useful. There are other ways in which it's useful. I'm happy to give further justification of that if you are currently unconvinced. And max filtering works well under the conditions of like you want it to be specifically fast in a particular sense, and you want it to be bilipschitz. And you also, I guess I needed to mention this earlier, you need your subgroup to be a subgroup of, or you need your group of symmetries to be a subgroup of your orthogonal group. If you're like talking about like scaling by any real number, then max filtering is not for you. And the key point of this talk, what I would say is the central point, it's the middle bullet point, or I guess it's actually the two middle bullet points, is that reflection groups can do the job even when they aren't the true symmetry. There was like a single slide about this, but it was also that textures picture that even if you're not exactly replicating your symmetry, working with reflection groups can encompass a broad enough set of symmetries that you still have the credibility and you're faster and you still have your classification. So that's the context in which reflection groups can work, and they do it fast because you can line things up independently of each other when you're working with reflection groups. It's a lot faster than anything when you're having to look at the interactions of your two groups. And so that's another valuable thing. And that's like why research into reflection groups and max filtering is useful, is these two bullet points. And then there's also this fun proof strategy that I think is really cool. I'm really just trying to convince everyone to use. And that's the last bullet point. It's the last thing I talked about today. So there are a couple future directions that we're working on, but I haven't thought about in a bit. And one is this general thing that we're doing with max filtering, which is trying to figure out what optimal templates look like in any context that's not reflection groups. This is very hard. I thought about it a bunch. It seems related to like ideas in frame theory, but I haven't been able to pin anything down yet. Happy to talk to someone about that. That would be cool. And also there's this like approximation move that I was doing earlier where we're taking one group and we're approximating with like a bunch of reflection groups. And it's unclear to me how we quantify that, but it feels like a thing to quantify. Maybe it's impossible. Maybe it's just like vibes. But if we want to like answer the stop sign question well, then we want something better than vibes. We want like real credibility there. So we got to figure that out. And then finally, this is something that I have not thought about at all, but people keep asking me, so I want to mention it in case maybe the other people are interested in working on it, which is, how do you extend this to complex reflection groups? I don't know anything about complex reflection groups, but if you know things about complex reflection groups, it'd be pretty cool to extend it to that. Importantly, the spectral property that I mentioned briefly does not hold for complex reflection groups. The spectral property is a result. I'm just going to say a bunch of fancy words now, so I'm sorry. If the thinking diagram of the reflection group is a tree, then the spectral property holds, and for certain complex reflection groups, it is not a tree. And so then you don't get those results. And so maybe interesting, maybe impossible to figure. I mean, not impossible, but like completely different to figure out how you do max filter over complex reflection groups. But yeah, that's, I believe, all my slides. Yeah, here are a bunch of citations. This is the scalable frames one that I didn't like have an inline reference to, but that's pretty cool. It's like short, sweet, solves a really cool problem very elegantly. Yeah, so that's my talk. Happy to take questions. Thanks y'all for listening. I hope you had a blast. I had a blast.
All right, well, if you had a blast, why don't you smash that reaction button? And we are now ready for